So we're opening afternoon session. Sasha Veselov, harmonic locus of Calogero-Moser spaces.
Okay.
Sasha, 1 hour.
Yeah. Thank you very much. This is a joint work with Giovanni Felder, which we did actually this April, and it's probably one of the most elementary talks. No, you think no? But it's related to many things. I think it's to almost all the courses we have heard, and I wish I can discuss this with Igor, as I did for many years, and I still feel a loss. I'm pretty sure that he will have some comments on this. So I knew Senya Schlossman mentioned that he knows for 50 years. I realized that I slightly less, but also for so many years. And Igor was one of my scientific brothers. When I joined Novikov School, he was referee for my final year project. He read and refereed my first work, and he gave me feedback. He gave me feedback actually in his flat, and we were very close. So I really missing him a lot. Now, this is Sergei Petrovich Novikov, the school of whom we joined. Unlike Igor, Sergei Petrovich, my first papers he gave me some problems, and my first 3 papers probably written on the topics which were suggested by him. I remember when one of the first actually topics was related to his work with Igor and Boris Dubrovin, and it was about two-dimensional Schrödinger equation, which we worked later on. And I remember when I asked him, when should we talk again, and he said, when you solve the problem, right? So he was, but he said the main thing, that you must attend the seminar, and this is how we met every week, right? And that's how the Novikov school worked, actually. It was a seminar, it was a walk-in, and we have to, it was actually proper communication, regular and very active life at the time. So this is our sadly one of the last photos where Boris Dubrovin was alive, and Igor, and Sergei Petrovich passed away, as you heard, probably 6th of June this year. So this was happy time in Ascona in Switzerland. So let me now talk about problem. Problem is kind of what is finite generalization of finite gap properties. I mean, if you ignore, so for example, if you consider rational solitons, they all singular. Spectral theory in this naive sense doesn't work. So the way how Moser, for example, and Adler did the problem, so rational soliton like 2 divided to x1 squared potential, it's singular. So you may deal with this, but the way Moser suggested, and he was inspired by Mark Grigorich Krein, you can shift real line in the complex domain, so it will become complex, the potential will become regular, but complex. So it's not self-adjoint. But the theory of non-self-adjoint operators with complex potential was also studied in the spectral theory. So this is the way. So the way I thought, so why? Because Sergei Petrovich Novikov contribution to soliton theory was mainly in periodic case. This paper is actually now is 50 years of his paper, periodic problem in Korteweg-de Vries for the de Vries equation. So because it's periodic, I thought that why should we move, why should not we go periodically, right? So consider time, or x, whatever is, and then it's naturally, you naturally come into the notion of monodromy-free potential, which is the following. So you have Schrodinger operator, one-dimensional, and yes, it's C, yes, yeah, Z in C. No, this is the thing. It should be C, of course. You're right. That's the first. That's the first mistake, right? Anyway, so so we want to have monodromy trivial. The main thing is that we demanding this for all energy, which is denoted here lambda, right? So so this is the problem. You consider certain class of, and this for me this is a kind of the most general generalization of finite gap property for some reason, which I maybe will be clear. So examples is all finite gap operators are monodromy-free. Why? Because remember Baker-Heser function from Sam Gruszewski talk, they are meromorphic. So the formula for Baker-Heser function is meromorphic, and therefore all solutions are meromorphic in they automatically. And so we don't use any properties of theta except that it's meromorphic. It's holomorphic, right? So the ratio is meromorphic. So but the history goes back. I mean, we did not know this. It was hidden somehow in the classical literature of 19th century, and actually the terminology also was confusing. I seen this in the paper. People in the classic in 19th century classified differential equation with uniform solution, and this is probably translation, English translation from French. There is a 6-volume book on differential equation. Remarkable book, by the way, a remarkable 6 books. If you want to know kind of classical analytic theory of differential equation, that's it's by Forsyth, and it's called uniform, and this is a uniform is actually single valued, which means that all solutions are single valued, no branching, and of course it's very much in favor of Pinlevier property and Pinlevier studies. So it's very classical actually. But it started with Lamé. Lamé example was the first, and Lamé equation was solved by Hermite, and then Halvan, Brionsky also actually. It was quite then. And then Darboux actually produced this P function, Calogero-Moser, with shift by half period, the most general one, and he explained how to solve it, what we later ascribed to Trébich-Verdier. This is all done in Darboux in a way, right? Because this part of mathematics was strangely enough forgotten. Pinlevier property, yes, it appeared and stayed because, but this one is. So anyway, it's a very classical thing, and it was modern theory. Probably should be attributed to Duistermaat and Gr. Duistermaat and Gr. it's hidden in their paper of 1986 about bispectral problem, right? But they have the following criteria. So after that, you may say that we are done. Everything is reduced to kind of algebraic equation. So what's the criteria? So you have V of Z with second order pole. Oops, sorry. With second order pole, and you can see the Laurent expansion near this second order pole, right? So then the condition when local monodromy is trivial is the following one. So first of all, C minus 2 coefficient at 1 over Z square must be twice triangular number, mm plus 1, where m is integer, and all odd coefficient, including residue, of course. All first m plus 1 coefficient should be 0, odd coefficient. It means that it's kind of quasi-invariant. Quasi-invariance. So if you consider reflection with respect to z naught, then it's invariant up to order z minus z naught to the power 2m. Okay, so it's invariant up to the high order, quasi-invariant. And this is if and only if, right? So it's very, in principle, after that, you can study this condition and that's it. It looks simple, but in fact, it's quite difficult. And what I'm going to explain is what the situation is in the one of the next simplest case. The first case, and that's also explained terminology, why we call locus, locus. So poles, if you, Harmonic and Moser in 1977 consider rational solution of Korteweg-de Vries equation, and they shown then that all the poles belong to the locus. Locus given by the algebraic, just a second, algebraic system like this. So what is this written here? This is actually equilibrium of Calogero-Moser system. Now, Calogero-Moser system on a real line is repulsive. So there are no equilibrium, of course. But we're talking about complex. Remember that this now we switched to complex Z, and therefore there are. And they explained that actually this, so we have algebraic system here, and we want to solve it. Now, here is kind of problem I'm thinking for a while. Suppose that we have integrable system, and Calogero-Moser is my favorite, and many other people like it a lot. So we know everything about that, and Nikita explained how to solve it, and this is actually will be. Now we're asking the following question. What's about equilibrium? We solved the problem, right? And now someone asked, do you know all the equilibrium? And if you solve the problem, the answer is expected to be yes. But it's algebraic system, and which it is integrable, right? It's a kind of philosophical question. If you consider stationary point of integrable, I don't know, good answer, but this all about this. And this is two examples. This will be first one. What's the answer here? The answer is, in this case, yes. And the answer is quite interesting. First of all, so we remember that we are talking about this simple algebraic equation. N equation on n variable z, and we want to solve this, right? So the answer is that it's arithmetic involved. If number of particles is not triangular number, it's empty. If n is triangular number, then it has dimension n, and moreover, it can be described explicitly. And explicitly, there are zeros of certain polynomials which were Birchnell-Chaundy. Remember lemma of Birchnell-Chaundy from Sam Gruszewski talk. That's next work. He cited, Birchnell and Chaundy studied commuting differential operator without any relation to spectral theory in 20s, right? Again, we did not know this. Igor Krichever had to rediscover a lot of this, but then, of course, contributed much more. So Birchnell and Chaundy, they in the 1928, I guess, describe the solution of this explicitly in terms of roots of special polynomials which depend on certain parameters. For example, look at this. So these are three particles. So this is root of unity, essentially, right? So the locus for three particle, which is the first triangular number, non-trivial, is actually equilateral triangle on a complex plane. Set of this locus consists of equilateral, which is nice. But if you think that it's going that simple, look at the next one, which is six particles, and they located. So you have parameter tau 2 and tau 3, and these are zeros. They depend on two parameters, are zeros of very special polynomials. Now these polynomials are sure polynomials actually in some variables, in some related to triangular Young diagram. So they have different interpretation, but still I like them a lot. And tau is actually time of high KdV, not quite. This is a very interesting. There is a very interesting part in Adler and Moser paper where they said that no. I mean, it's actually there is a polynomial triangular transformation, which is quite remarkable. It's not. This parameter tau is not strictly speaking KdV. KdV, yes. Yes, that's what next. That will be. Right. Sorry? Right. That's exactly next step. Right. So this is what I'd like to do exactly. The whole talk is about exactly this problem, right? And this is the problem. I thought it's easy, and I gave it to Alexei Oblomkov, who was fourth year student at the time, and he did solve it. But it turned out to be much harder because he was very good student, right? And he did solve it, but to me it was in kind of unsatisfactory way. Now, but let me first say that what we have here, if multiplicity are 1, then these are Duistermaat and Gr condition, and they again equilibrium of Calogero-Moser in the harmonic field, external harmonic field. So you have n particles, but they now inside harmonic field. That's why it's harmonic locus, just for short. So we would like harmonic locus is the monodromy-free potential of this form, if all multiplicity are 1, then it's called simple part. But we will see that it's. Then you have this equation, and this in this complex equilibrium of Calogero-Moser system, right? And this is the answer which Nikita hinted. All such potential can be explicitly described via Wronskian of Hermite polynomials. If you consider real equilibrium, then it was known since Stieltjes. It's 19th century again. The zeros of, it's called electrostatic interpretation of zeros of orthogonal polynomials. It's this, well, not quite. It's the equivalence to Stieltjes is not obvious. And that's, but anyway, the result is that if you have repulsive particle on a line inside of harmonic field, then the particle will settle at the zeros of Hermite polynomial. And these zeros are real, and these are the all real equilibrium. we're interested in the complex. In the complex, the answer is given by, you have to consider Wronskian of Hermite polynomials. Let me now just say a few words about Hermite polynomials. They correspond to the Gaussian weight of e to the minus z square. And they are, in a way, simplest and nicest and most probably studied polynomials. And of course, they appear in random matrix theory. But actually, look at the coefficient. The coefficient are, in certain normalization, you can make it monic. And they're integer polynomials. And then the person who studied them first there is a lot of number theory here. You may ask, these polynomials are irreducible over Q? And of course, for odd polynomial, it's certainly not true because they're divisible by Z. But if you divide odd polynomials by Z and consider even polynomials, Isaiah sure proved that they are irreducible over Q. And this is a kind of result which is unexpected. You won't normally ask in number theoretic question about orthogonal polynomials, but here, because of normalization, it's very, very deep, very, very interesting set of polynomials, probably the most. And they have the simplest recurrence relation, which will actually play the role, of course, later on. Now, for us, it is important that this is called Darboux transformation, which is one of the technique in integrable system how to produce, if you know, one integrable, or in our case, monodromy-free. Then you factorize it, you swap the order, it's called Darboux transformation. And because swapping the order is semi-conjugation, you can, if everything is meromorphic, then the new potential, the new operator will also be monodromy-free. And this is a kind of, this was essentially Darboux invented, as I understand, he was motivated exactly this question. He was not motivated by spectral theory. He was motivated by strangely enough, this, but everything comes from, inspired by Hermite's study of Lamé. Study of Lamé was very influential and moved many people. So, and therefore, that's why, and if iteration of Darboux transformation is expressed in terms of Wronskian, and that's why all the results of. So let's now. So this was so Alyosha Oblomkov proved that they all must be. So one way it's obvious, another way it's non-trivial, and actually proof. I think we should try to simplify it and actually make it more effective. Part of this job I'm going to do is now done, but still. So we started with Giovanni Felder and my PhD student Adrian Hemery, this Wronskian. And it's, we label them by partition. And so, this is how we should label them. So these are clearly different numbers, and so you can label them like this. It's kind of shift by row, if you want. And in this parameterization, they have quite natural property. First of all, the degree is exactly lambda, which is sum of lambda. They have parity, which depends on this. And this is nice property because it was, if you consider conjugate partition, which is a lot of course, conjugate partition, if you have a lot of, it's very different. Wronskian will be very different because partition changing the number of rows, right? Sorry, involution change. But it turned out to be that it's just multiplication by I, Z, right? And it's also a real one, but it has, instead of 4z squared minus 2, you have 4z squared plus 2, for example, if you consider. You're absolutely right. No, but I mean, but the relation is z to iz, if you look at this. So it's kind of, transposition of diagram, it's a kind of rotation of I. Okay. Now, but the most remarkable observation we made was for double partition. Suppose that we have partition which is doubled, and we say that lambda 1 repeated twice. Then we can draw partition like this. Not, there is usually, what is it, British way, French way, and we all four here, right? If we put all four here, then, sorry? Exactly, right, 45 degree. So this is the thing. Then we realized that in that case, look at the position, for example, for this particular Young diagram, where 4, 4, 6, 6, text 10, 10, right? I mean, then these are zeros, right? So you can see 4, 4, 6, 6, 10, 10. Now, this is just empirical observation which worked in many, many examples. So you have, it looks like you can see, looking at the locus, corresponding locus, we can see the shape of diagram. But in general, it's not so clear. So if you consider random partition, not double partition, 26, then look at that. I mean, it's not, there is no, it looks like, they look like, you cannot read off these numbers, at least we can't see the rule here, right? So that was exactly my question. My question was, suppose that now I'm given monodromy-free potential, something like this, right? And I'm asked, what is the partition? What is the partition? So this is the question we discussed it with Alexei, but I mean, it was difficult. Now, I had actually an idea, and this idea, so suppose that we know set of zero set of W lambda, which are poles of this monodromy-free. That's exactly harmonic locus. I'd like to call this red set point harmonic locus if corresponding potential is monodromy-free, right? So this is, so now I have to introduce Leningrad way, which is in fact Frobenius, right? So Frobenius notation is this kind of thing, related to at least. So there is a content. So if you consider Young diagram, right, and we write content of the box is j minus I. So 0 on the diagonal, minus 1, minus 2, here 1, 2, 3, 1. Okay, so this is content. And content appeared in a paper of Vershik and Andrei Kunkov, for example, in the description, in this approach to representation theory of symmetric group based on Eustace Murphy. Right, it's a paper. So content is appeared in many relation, right? So it's not now this is our theorem now. So how to recover Young diagram from the locus? We consider Moser matrix M, which appeared in, I think, in Nikita's paper. So talk, which is so we of diagonal is, so we have Z1, Zn, and we exercise. So we have 1 over Zi minus Zj square, but there will be something. Yeah, I will say something. This is the case of colliding particles. Right. Yes. Actually, Nikita hinted in his lectures. It's imaginary. Anyway, it's minus Zi minus Zj. And on diagonal is defined, so it's very, very simple matrix. You put minus 1 over Zi minus Zj square at ij place. And on the diagonal, you put numbers such that 1, 1, 1, 1, 1 vector, which appeared also in Nikita's thing, is in the kernel of this. No, I mean, we wanted to guarantee that at least we have 0, right? One, 1, 1 is kernel, in the kernel. But you see that it's as many kernel, as many as on the diagonal, right? So one of them. And actually, my first attempt to prove this conjecture was based on we put in the corner 1, 1, 1, and maybe acting kind of raising and lowering operators. It doesn't work. They don't compute, and well, we didn't manage. So, and with Giovanni also we start with this. But instead, it turned out that its theory of Calogero-Moser spaces of George Wilson helped a lot. So what is, but let me, this I can do briefly because Nikita explained this very well. So the only thing I would like to, so you have, I put gamma square here for a moment. And usually gamma is real. But, and then particles are repulsive. Now it's, and then L matrix is Hermitian. Because you have I here, and this is L matrix, and this is M matrix. So this is off diagonal term, and this is, but you see I here, and you didn't see I in my. Why? Because George Wilson, who wanted to consider collision of particle, he said that we should put negative sign. Let's make them attractive. Then Calogero-Moser particle want to collide. And let's study collision. And he has written a very, very influential paper, actually, which I knew somehow, but didn't appreciate until now, right? I mean, so it's followed by Kazhdan, after this seminal work of Moser, Kazhdan, Kostin, Sternberg had provided explanation using symplectic reduction, which Nikita nicely explained, and so I'll maybe skip this. What I wanted to mention is important contribution of Askold Mikhailovich Perelomov. Actually, there is a preprint which I couldn't find, 1976. I tried to find, I thought that it's, because it's, so this is published version, right? So I think I learned many of this stuff from that preprint, but I couldn't find it. I couldn't check. So anyway, we might try to find this preprint. I have a number and the year, but anyway. So if you have harmonic version, if you have x square, then lux is deformed like this. You have plus minus L plus minus, right? And then if you multiply, for example, L plus and L minus, where L is L plus minus Q. Q is simply matrix with Q on the diagonal. Q is matrix. P is, so there will be L matrix, which is the most important Moser matrix L, which is M matrix, which is most important for us, which is second Moser matrix, and there will be a kind of trivial matrix Q, which is simply Q on the diagonal. So these are three matrices which will play the most important role, right? And Perelomov observation is that if you consider L plus minus, if you do, and then you have this, it means that if you multiply L plus times L minus, then you have a proper Lux representation, and you can construct integrals, and this is complete integrability. But it can be also solved explicitly. But the most important for us is that if you look at this. If you look at now equilibriums, what is written here, L plus minus M plus minus L plus minus equal to 0. So M is like raising operator, right? L is raising operator for M, and L minus is lowering operator. Right? But it acts on exactly on the locus. Okay. So now back to George Wilson. 1998 paper, which is called Collision of Calogero-Moser particle and Calogero-Moser spaces, right? And he introduced Calogero-Moser space, which is a kind of generalization of what we see. So it's a pair of matrices X and Z. Again, it appeared in Nikita, so I might not. So X is right. So let me go back maybe. Although Nikita explained, but I'd like to remind you. So let's consider commutator of L and Q. When you consider commutator of matrix with diagonal matrix, you multiply all of diagonal elements by Qi minus Qj, right? Qi are one. So in that case, you have just matrix with I gamma. 1, 1, 1, 1, 1 times I gamma. So, and 0 on the diagonal, right? Which is rank 1 minus identity. Okay? So commutator of L and Q on the diagonal, you have 0, of course, because you commute with diagonal matrix. Of diagonal, you have all elements 1 essentially up to I gamma, which is 1, 1, 1, 1, 1 matrix consisted only 1, 1, 1 minus diagonal, which is identity. Okay? So its commutator is almost identity plus rank 1. This is exactly, that was known, of course, after Kazhdan, Kost, and Sterbeck. So little change, but substantial. He changed unitary group by SL and Z, SL and C, and makes everything complex and consider this. So this is Calogero-Moser space. It's a pair of matrices X and Z, complex matrices, any, such that they are minus identity plus rank 1. VW is a kind of, we can view them, it's vector and covector, and if we multiply them, we have matrix of rank 1, right? So this is the thing. And GLN naturally acting on these matrices, and matrices as it used to be, and vector and covectors are also. And then, and what George proved is that this is quite interesting. It's a particular case of Nakajima variety, but very special one maybe. So it's a smooth, irreducible, affine algebraic variety. If you remember what Sasha Braverman said, that normally this Nakajima variety are affine, but sometimes it's projective over affine. So, but because it's, and this is actually Happer-Keller, so you can rotate. Yeah, right, morally. Of course, yeah, right. But what I want to say is that the quantization in the sense that if I put X and Z equal to 0, yeah, quantization, I plan to put in moral. What? That's correct. But what I wanted to say is actually weak. It's like a moral quantization because I replace xz equal to 0, but xz equal to 1, right? It's impossible because trace, so we correct him by minimal correction is rank 1, and this is, yeah, and there is a very important interpretation of this space in terms of, yeah, right. Yeah. But this is, yeah, this is a kind of, yeah, Nikita and Schwartz paper that the general idea that quantization kind of removing singularity. This here, if you consider x and z equal to 0, you will have Hilbert scheme and you have to resolve singularity. Here, that's Wilson proof that there are no singularity. GLN acting free, everything is fine, and this is the kind of thing, right? And what's important for us is that there is a natural symplectic action of C star here. Namely, you multiply x by mu and z by mu minus 1. And it's clearly that it's symplectic. And let's consider fixed point set of this. And Wilson identify this set with set of all partition of n, right? Which kind of ring the bell because this is kind of, and you will see that we realized that this is the same set somehow. So what we did, we introduced, just took what we had from harmonic locus, and in harmonic locus we had L and Q is moral x and z, Wilson, but we added M. M is and M is actually, so if, yeah, so which satisfy, so this is a generalization. Modified Calogero-Moser space is 5 matrices which satisfy this relation. The first one is the same as kind of similar to Wilson, but we have matrix M, which is, you remember that 1, 1, 1, 1 was in the kernel and in the kernel. So this is the thing, and this means that you see here that it's acting like generator of this symplectic group, and therefore so this is the main result. So this modified Calogero-Moser space is actually much simpler. It's discrete, but it's parameterized by partition. So from combinatorial point of view, it's very nice. It can be identified with the set of all partition of n, right? And it can be identified with harmonic locus simply by explicit formula like this. So this is alternative description of all yes.
Simple way of describing these four equations is just a critical point of one function, which is n times the trace of n times the small trace n times the first equation.
I see. Yeah, I mean, it's the thing is that I see, right. So anyway, it's the fact that fortunately this set was explicitly described by Wilson, right? So everything was ready for us. But let me skip explain this the sketch, the proof. Sorry. Oh, it's not. It's unfortunately not. It's bad notation. We had we ran out of Greek letters and we use chi, right? Which is just a map from modified Calogero-Moser space to harmonic locus. It's called chi here. Okay, so chi of this LQM point. It's just explicit formula. Pi is over there. It's just phi. Right. No, I mean, it's just notation. So it's just a map, identification between stationary point and in this and this. And Calogero-Moser. That's alternative way instead of Wronskian of harmonic of Hermite polynomials. But let me, the proof is quite nice. So first of all, we identify this with fixed set, and this is Wilson's x and z. That's simple, trivial. The second observation is that M is generators of C star for x and z, it's acting like this, which is exactly as symplectic action, and then we use the actually appendix to George Wilson paper is written by MacDonald, and this part I think George derived himself, but a kind of MacDonald suggested more elegant way to prove some lemmas from George Wilson paper. So there is a relation with sure symmetric function, and then step 4, there is this theory of Appel polynomials. So how Wronskian appear? There is some general result which we using this recurrence relation for, well, generating function actually for Hermite polynomials. We have this formula which is exactly one of the formula, and with harmonic locus, after we reduce it to Hermite polynomials, we use an Oblomkov theorem. That's all harmonic locus. That's it. Identification. So it's not obvious in a way this identification. So now back to reconstruction, inverse Wronskian problem, right? Suppose remember that we have zero set of Wronskian. We want to know which what is corresponding lambda diagram. What are the corresponding set of this? And the answer is that this is content multiset. Now Moser matrices, obviously I checked some of this already, and especially 4. I mean they all satisfied, and we have one. And but the identification using explicit description from Wilson, right? He explicitly described this stationary point. It's nilpotent. It's kind of most degenerate when all particles collide. So partition describing Jordan block structure essentially, but he did it very well in such a way that user friendly. So he used even Frobenius parameterization of lambda to make it this is easy. Okay, so I must say that Calogero et al., and I think it's this is related to Stiltius, but strictly speaking, it's different of Stiltius. So if we this is I think Veselov is one of the co-authors of this paper, but Calogero was fascinated by this result. He made a lot of so matrix M defined by zeros of Hermite polynomials has eigenvalue 0 and -1, which are of course content of string. But so this result was known. Somehow it was also motivation for just to replace it by contents here. So it was natural. But one thing we are very happy, because there was one result which we could not prove. There was paper inspired by Bazhanov, Lukyanov, and Samolotchikov, monster potential. I will mention this, and they it was studied by Conti and Massaero. And this is the following problem, which was also studied by Perelomov. Let's consider this equilibrium, and let's consider corresponding frequencies. Of course, it's a bit stupid, maybe because it's complex. Everything is complex. What is the? It turned out, but we formally consider Hessian of potential. Okay, and Perelomov had a very nice observation that even for generalized Alshanevsky, Perelomov, Calogero-Moser system, they are related to exponent of corresponding Lie algebra. Right? There was a kind of thing, but this case is AM. But this was only for real equilibrium, for zeros of Hermite polynomials. And now we have Wronskian, right? We have now Young diagram. For the Young diagram, which is just row, Perelomov said that the answer is 1 square frequency are 1 to n. That's very long, beautiful paper actually. This is equivalent actually to Conti-Moser. Conti-Moser described recursive way to compute these eigenvalues, right? And we prove the following. Look at this formula. The spectrum is tricky here. It's again labeled by boxes in Venn diagram. But look at now. Now you have content combination, and this was very puzzling for us. Lambda of leg of box plus 1. I never seen such a formula, right? So we stuck at this point for the last week. We tried to understand. We first thought that it could not be true, but I mean but then we checked in the it worked, and we started to look for the proof, and we managed to do this. And for this, you have to consider just definition essentially, action of this symplectic exact sequence, and then you compute this, and using Wilson result, we prove this. So this is indeed true. So and as I said, in the case for rho, this is and the fact that they are square of integer means is kind of corollary of the fact that all orbits are periodic, of course, in this case, right, in harmonic case. So this is, but this is quite peculiar. I'm still puzzled by this formula, and the most how Conti and Moser were able to guess it. To me, it's without deriving this. It's quite so. We were very happy that we managed to prove this formula. Anyway, just few last comments. So what are the, okay, go back to, let's go with locus problem. Description of monodromy-free potential. So essentially, it's easier to list all the problem which is solved. Rational potential decaying at infinity. That's Duistermaat, Grünbaum, Rho-Moser. Quadratically growing potential, x squared plus decaying. That's Oblomkov and our contribution to this. But for trigonometric locus, where we can also use Darboux, and this it's for example inverse. One way we have description, but inverse problem is difficult. Most interesting probably elliptic locus. Elliptic locus is it was very important question which Sergei Petrovich Novikov raised many times. Igor contributed to this. Describe finite gap potential which can be expressed in terms of elliptic function. Actually, the very first paper, Dubrovin-Novikov 1974, JET paper, they took 6 p function and split it into 3, and you have 3 elliptic p functions shifted cleverly so that this is the thing. But in that case, spectral curve is the same as Lamé. So for elliptic locus, I think the question is probably kind of number theoretic. It looks quite difficult. Although I did discuss it with Sam Gruszewski, and he did not say that it's hopeless, right, about this problem, because this is a question when in hyperelliptic Jacobian, you vector passing through 2. I mean, that's Igor always said that. What's the point? Well, when it happened, for which curves, and this is very, very delicate thing, because U vector is very special. It has to pass. Anyway, so it may be not hopeless, at least. I mean, I thought that Sam would be pessimistic, but he was not. But anyway. and then this is one of the outstanding conjectures in this area. Yeah. It's by Bazhanov, Lukyanov, Zamolodchikov. They have very interesting conjecture. They counting this kind of what they call monster potential, which are nothing but monodromy-free potential of this form, where when alpha is 1, then you have a particular case. You see that z to the 4, it's invariant under rotation. It's a special Venn diagram which are symmetric under conjugation. So, and they count in them, and their conjecture is that it's the number of this is the number of partition. So the best would be probably to establish again some identification with partition. But anyway, so this is actually one of the problem. That's exactly was Conti and Massoero paper dedicated to classification of Massoero, and then they looked at a related problem, which was this locus problem. But this is a particular locus problem, and we were interested mostly in Hadamard problem and Huygens principle, which is related to multidimensional Schrödinger equation. And finally, this is a reference to our paper, which is now on the archive. Thank you very much. Gosh. Just a second. Turn on? Yes.
The bijection chi sends a list of matrices to the potential, but the I can see that chi only actually depends on Q. So this means that the list of matrices can be recovered by Q.
The set is discrete, right? So you have what we have LMQ, right?
Yes.
So and there is only one Q for pair of L and M, but it's not natural to label just by Q, because the identification is that there is this modified Calogero-Moser spaces, which is the full set, and the formula for the potential using only Q, but this happened to be the case. It's like formula. There is a formula for Baker-Heiser function in Wilson paper, which is beautiful, by the way. Also written, it's e to the xz, and then 1 plus inverse of written in terms of x and z, but certain combination only. It's always, the answer is depend only on Q, yes. But you need, to describe the set, you need all 5.
Oh, and for the last open problem, the Hadamard problem is for hyperbolic equation, and here we have time-independent Schrödinger equation.
Yes. That's true. I mean, strictly speaking, this is A, real, B, hyperbolic equation rather than Schrödinger equation. But as we showed, there is a natural complex generalization, which is essentially monodromy-free property. So morally, you have 3 things. First of all, Huygens principle, which means that no reflectionless property for solitons, no reflection. It's a kind of, because any reflection destroys Huygens principle. You have echo, right? But soliton equation are exactly, those are reflectionless, but it turned out that they still destroy Huygens principle property. So it's only rational. That's this showed the role of the rational degeneration. Only rational degeneration of solitons appear in the theory of we don't understand why it happened. No elliptic, for example, appear in this theory, but maybe there are reasons for that.
And is it related to the quantum case of Calogero-Moser system?
Yes, yes, yes.
Ah, okay.
Can you go to the first one slide at the beginning where you plot some probably zeros?
Yes, yes. Just a second. Yeah, maybe I should. Oops, just a second. Can I? This is still puzzling.
Yeah, can you say again what was plotted?
The problem is that you take any partition, you write down corresponding Wronskian of Hermite polynomials, and then you draw the set of zeros. The question is how to go from set of zeros to back to partition. And in the case of double partition, we had a remarkable phenomena which we don't have good explanation. And moreover, it's destroyed badly if you go out of this double partition. So that's why we had to do something else, namely consider matrix M, look at the eigenvalues, because and the eigenvalues give you set of contents, and set of contents uniquely determine lambda. That's the important thing I forgot to mention. If you know set of contents of Young diagram, you know the Young diagram. Right, so the spectrum of M is defined. Rather than looking at the picture, right, we had to do linear algebra calculation. Right? But this is a kind of phenomena which is strangely related to what Senny Schlossman was talking about. He had integer matrices with integer eigenvalues, which is also a miracle. And here you have algebraic numbers, and still integer, right? But there must be reason for this.
Maybe if you plot a discriminant curve, it looks nicer. I don't know.
Discrete character.
Discriminant curve.
Discriminant character.
Because you have repetitive edges.
Discriminant character, which is coincident root lossy kind of thing, right? Maybe.
What can you say about the stability of those equilibria if that question is correctly defined on a complex plane at all?
So you see, this is the problem. It's complex dynamics, right? We were thinking at this. What does it mean that? But it's kind of, everything is complex. All our intuition, about stability is real dynamics. Here it's complex dynamics. PQ are complex. So, but nevertheless, you see that we compute in Hessian, it's complex matrix, and it has integer squares of integers, right? So kind of, we still have frequencies. But of course, they are characters of action of C star, right, in this case. But I'm not sure if we should talk about stability. Rather, it's action of C star, right? And real time is S1 in this, and then so it's periodic. Real time we can make real.